Hey guys, I may have actually fixed this. I'm not sure, but I hope. I mean, I don't know, I've been trying for a while and yeah. So, yeah, today there's round 725. I'm just going to go for it. Still in the position I is anti-power AI. Powers of all stones are distinct. Destroy stone on first or last. Gets them if he destroys the stone with the least power and the greatest power. Okay, so we find them. Okay, so we're reading test cases and then x plus 1 plus n minus y. It should work. Oh wait. Min. So minimum of y plus 1, n minus x, and that. So either we do all on one side, all on the other side, or sort of like crunch. 2, 4, 5, 3, 2. Okay, I have too much stuff. Oh, shoot. No. God damn. Alright. It's kind of a mess. Okay. It's n friends, the nth friend has AI candies. Choose k arbitrary friends, distributes to k candies. He wants them to all be the same. Okay. So if the average is not if not an integer, then there's no answer because they have to all be equal. AI is greater than S over N plus C. And otherwise, we have to redistribute from everything that has a larger value than the average. What am I printing? Oh. Alright, we're good. Let's continue. Okay. Given an array of n integers, find the number of pairs, the sum. Bro, really? Seriously? Okay. Let's just do it. Yeah, I mean, I don't have much more to say. So what I'm going to do is I'm going to pull out the ordered set because that's probably the easiest thing to do. Hopefully it doesn't TLE on me. So really just counting this. Okay. So we want between L and R. So subtract AI from both of them. Then R minus AI. Rance plus equals OS dot order of key. So it's R minus AI plus 1. L minus AI. In fact, I don't even need a sort, but whatever. Yeah, I don't need a sort. That's okay. So R minus AI plus 1 because we need to be inclusive, and then we're exclusive at the end because we need to, no, we're inclusive at the end. Yeah. Hopefully this doesn't have TL problems. I don't think it should. What? How? Oh, there you go. Okay. I'm so dumb. That was lame. Okay, another problem about dividing numbers. Take an integer c and divide by c. A equal to b using exactly k turns. Exactly k turns? Okay, so we prime factorize the numbers. We find a lower bound and upper bound and check if k is within the... God. I always mess something up. Just always. Just always. Okay, now we need to run the number theory stuff. So I need the prime factors. Lower bound and then extra 0. So we're looking for pairs that are in A but not in B. If so, mb.find x.first is equal to mb.end. So it's not in B. lb plus equals x.s. Do the same thing for B. These are things we have to remove to make them equal. But now we do it again, except now we're looking for things that are among both. So lb plus equals abs mb x.f. So it should be the absolute value between this count and that, because first we have to make them equal, and then for extra moves, we can do 2 at a time, and we can Yeah, do that. Wait, is there even a lower bound? Oh, never mind. There isn't even a lower bound. We can just do it in... Yeah, that's the number of moves we can make. Do they guarantee that k is greater than 1? No, they do not. So that's annoying. That's very annoying. Oh my god, okay. So we're going to check first if x that is so annoying. So then I'm looking for the number of extra moves we can do. I guess like any amount is fine. Yeah. And I need to not be equal. Extra plus equals. Wait, is that just the sum of the prime factors? Wait, is it just the sum of the prime factors? Because within 2 moves we can do whatever we want to. Actually, in every move we have to kill at least 1 prime factor. But other than that, we basically get free reign. So maybe it just is like... I think it might just be that. What are the values? We have the 10 and the 9th, I think that's fine. Nice, what's with that? Oh, should be greater than or equal to k. Yeah, I think so. It's kind of close. 2 seconds, alright. This is easier. You're given 2 integers, L and R. We'll add 1 to L till the result is equal to R. This is probably standard. Yeah, it is. So we look at each digit. Every time, like for example, the second digit changes, then 2 of the things will change. Every time it changes from 9. Look at the number of times this digit will change. So initially we get R minus L, of course. So So now we're interested in the number of times this crosses 9, right? So it's like for example, if we have 15 and 24, it'll cross once, right? Oh wait, it's just every time this increments. Yeah, every time this increments. Ants plus equals y minus x. It's every time it increments, it will flip a suffix, so we get some extra like values. Okay, that's simple. I hope. Where are we now? Okay, if only you didn't have that penalty. Damn. Gift set. X of red and Y of blue candies. Using them, we want to make gift sets. A red candies or B blue candies. Or A blue candies and B red candies. Okay. Yeah, I see. Which one has more souls? E or G at this point? E doesn't have any souls. Okay. So, how's this work then? Guess I'm behind on penalty. Being second is pretty cool though. So how does this work? So we're fixing like the number of one type of set, maybe the number of the other type. Maybe it's just like ternary search. If we spend the fixed costs. Alright, we can binary search in the answer. Okay, I think this works. Yeah, so we spend the minimum of A and B automatically, and then we basically have like one of them will have 0 extra and the other will have like B minus A extra. So if A is greater than B, swap. Okay, now RB equals 0, RB equals 9. Nine plus 7, why not? Some bigger number, bigger than 189. XX minus equals A times MB. Y minus equals B times MB. If XX so if now XX divided by B plus YY divided by B less than MB, pos equals 0. If pos go higher, LV is equal to MB plus 1, RV equals MB. Might have to subtract 1 from the answer here. What? What? That doesn't make sense. Okay. Why is that happening? So 10, 12, 2, and 5. So if we dictate that we're going to do 3. Then we subtract 2 from each of them. Oh, wait. Right. B minus A should be it. That could crash, actually. Yeah, that could crash. That will almost certainly crash. If B is greater than A, then we check that. What? It's sometimes larger? How? So 1, 1, 2, 2, the answer is 0. Why do we get 1 then? Alright. So I do need to do this, but then that breaks it elsewhere. So for example here, with 2, 3 should be possible, because we say we do 3. So we have 4 and 6. So what's the deal? Oh wait, why would I subtract B here? That doesn't even make sense. Three, 0, 4, 1, 5, 0. Okay, now it makes sense. Now it all makes sense. Wow. Let it be known, I'm winning this. I'm not gonna win because Neil has a better penalty, but if not for this, I would be in a position to win this round. Damn. Let's do E. Funny substrings. Okay. Assign the variable named X the value S. Concatenate A and B. Still in first, yeah? Or have I lost that already? Yeah, I've lost it already. Okay. Wow, yeah, he saw that instantly. Okay. So set X to S. Or set it to a concatenation. Okay. Really? Actually, oh my god. What the hell is this? What is this? What is this? Oh my god. They guarantee that. Okay. This is stupid. So map string parallel string. Because we're counting ha-has, we only need to maintain like the. Actually, yeah, 5 characters is about right. We only need to maintain the first and last 5 characters. String MP CN to N. Last equal to A, then cout mp last. Okay, so if this is that, then string shrink. Okay, so does this work already? Okay. Then we need a mid. For I plus 3 is less than s dot length. Okay, now what we need to do is check the indexing. So if the interval wait, okay. So the first thing we do, min 0 should be m minus 3. No, should be m minus 2. We're only checking for new ha-has. So m minus 2. Should be max. Right? So m minus 2 because we need to contain that, and m because we need to contain it as well. So there really should only be 3 substrings, and this makes sense because, yeah. Okay. So LV I less than equal to RV I plus plus. If s dot length is less than equal to 10, else t is equal to s dot substring, the first 5 characters plus the last 5 characters. Because when we're considering new strings, we don't need anything else. And in fact, 5 is an upper estimate, but because there aren't that many operations, it's fine. In fact, we do need to do this because it could be exponential, but whatever. S dot substring 0, 5 plus s dot substring, what would it be? So it'd be s dot length minus 5 and then 5. Return, yeah, it's t. MPA is equal to shrink C. X is equal to MPC, Y is equal to MPE, and it's equal to X dot F plus Y dot F. Shrink X dot S plus Y dot S. MPA is equal to pair of ants plus Z dot F, Z dot S. Okay, no way this works, but shrink C and then 2. Or rather, C dot length over 2. Should should be inclusive of everything. Yeah, that'll always be part of it. S dot length. So if we used either one as mid, should be fine. It's messes with the indexing a bit. It actually works. Do I trust it then? So we add them, then we shrink them. And suppose z dot f, z dot s. They guarantee that the answer. Oh wait, it's 2 to the 50th. Okay, that's fine. Yeah. Seems like it'll work. M minus 2, s dot length minus 1. M. And then shrink that. I mean, yeah. Seems like it should work. Oh wait, I should be careful here. So if I plus 4. Oh yeah, okay. Let's check that too. I plus 4 is less than or equal to s dot length. Right? So I is 1, the length is 5, that's fine. I is 2, the length is 5, that's not fine. Yeah, actually that would be important. Okay. I mean, I don't know. Cool. Alright, I guess that settles it. So this penalty made like a tiny difference, but I guess not that much. And no one else can beat me. So I guess we're solid 4th. That's pretty good. Beats last time where I got 5th and then lost it. Great. Yeah, alright. So what could have gone better? Let's find out. So if how much time did this take? Let's go to my submissions. I mean, it could have saved me a little bit. But also, like, not that much, I guess. Wait up. It would have saved me 37 seconds. Actually, I think that would put me at exactly 94. That's kind of funny. Well, whatever. It is what it is, and yeah, I wouldn't have beaten Neo anyway. But that's still cool, 4th. And because some time has passed, how much time has passed? How long was the contest? Okay, so 35 minutes in, so therefore nobody else can get a higher score, right? Or 35, 70, no, nobody else. Cool. Beaten LGN. Yeah. Alright, so overall view of the contest, I guess I can talk about each problem individually. The balance, as you can see, F was like a lot more standard than expected, I guess. G was, I don't know. So A was just whatever, implementation. B B was also sort of implementation. I guess everything is. This one tripped me up because of equal values. I don't know what to comment on that. This one was actually okay. It was more elegant than I thought it would be, so that's cool. I don't know how it took. Ten to the fourth. 10 to the fourth. Hopefully they have like a single strong test with factorization. I hope. 10 to the fourth is like, I guess it's okay. I don't know. I mean, I guess. Let's see, this one was fine. It's kind of annoying, but also like, ended up not being that bad. Solely because I didn't get wrong answer. If I had gotten wrong answer, my opinion would have differed a lot, but I didn't, so cool. This one's very standard, I guess. Kind of. Sort of an idea that I've seen before. And in fact, I might have even like seen a very similar problem to that, like almost the same problem or something. I don't really know. And G was also something. I don't know what to say about this. A lot of these were standard, and that's sort of like by design, right? But yeah, that's how it goes. Okay, well, in terms of solve order, it would have actually been better for me to solve F before D, but whatever. Hello. Okay, I'm going to do solutions now because I sort of have to fix something up otherwise. Yeah, okay. So I will do solutions. Hopefully this thing worked. That was loud, wasn't it? I just wanted to test if the microphone actually picked that up. If that hurt your ears, I'm sorry. I just wanted to like make sure it was. I wanted to make sure it was this microphone and not the laptop microphone that you may or may not be familiar with. Well, that does seem like the average like audio pickup is a lot more. Like it's usually it was around here, but now it's like all the way over here, so that's great. I did do the microphone boosting as was suggested. I didn't realize that was possible, but like it was like slightly confusing interface, but yeah, it's fine. If it's too loud, then that's fine because you can turn your volume down, but I'll find some calibration later. Okay, so A, you have a bunch of stones, like, for example, 1, 5, 4, 3, 2. In one move, you can either remove a stone from the left end or from the right end, and you want to remove the stones 1 and n. And you want to find the minimum number of removals it takes. So there are basically three possibilities. Well, first you find the location of 1, call it A, and you find the location of n, call it B. And then it's easier to sort of like think about the smaller one and the larger one, so we can assume that like A is like less than B, and then if A is greater than B, then swap them so that A is less than B. So then there are three possibilities. One, we remove only from the left, in which case the answer is B. Or I'm going to use zero indexing. The array will be indexed like this. So in this case, the answer would be b plus 1. We need to remove the first b plus 1 elements. Or we remove only from the right. In this case, it's going to be all of this, so it's obviously not optimal for this one. But in this case, it would be n minus a. We remove 5 minus 0, we remove everything. Or we can remove some from the left and some from the right. In which case the answer is the number we remove from the left, which is a plus 1, plus the number we remove from the right, which is m minus b. And these are like the only cases, because like what else would we do? There's no reason to remove any elements between a and b if we're coming from the left and the right. And we've already considered the case where we only remove from the left and only from the right. So that basically handles everything. So the answer then is the minimum of these three. That's not how you draw that. Yeah. And so the implementation is simply finding them, and then we just check these three cases and print the minimum of them. And I'm using this bracket notation because minimum will also allow you to take in like a vector or something, and so it'll give you the minimum over that vector. Actually, I'm not sure what this data type is, but it's a nice like syntactic sugar. But yeah, that basically handles everything. I called them x and y instead of a and b, but it's the same idea. Okay, for problem B, essentially you have some friends and they have some candies. And what you want to do is you want to pick some subset of friends. Like for example, these three, which is not optimal, but you'll pick some subset of friends and then you take all the candies from them, which is sort of mean, but then you'll do better. So you take all the candies from them, and then you redistribute the candies among any of the friends, not just the chosen ones, however you want. So for example, if I want to redistribute, I can give like 5 to this guy, and then 3 to this guy, and then 4 to this guy, and none to this guy. Notice that you can even like give candies back to the person who you took them from. So like there's no restrictions. There's no restrictions on how you distribute the candies. What you want to do is you want to distribute it in a way so that every friend has an equal amount of candies. So one way to do that would be to, in fact, I'm going to keep that. Then I just give 4 to everyone, and then everyone has 4. So the question is, because you want your friends to be happy, what's the minimum number of friends you have to take all the candies from to still make the like redistribution work? So how many friends do I have to take all the candies from so that when I redistribute, I can make everything equal? In this case, the answer is 2. We can take from the 2 5s. That gives us 10. Then we redistribute 4, an extra 2 for this guy, and 4. And that way, everyone will have 4. And it's also possible that it may not be possible to do that, in which case you would print -1. So the non-possibility case is because everything has to have the same element. We consider like this variable s is the sum of ai, like the total number of candies everyone has. And then if s is not divisible by n, then it means like the average value isn't an integer. And because we need everything to be the average, it has to be an integer or we'll just like, it won't be possible. So if s is not divisible by n, then the answer is -1. No answer. Because like say we had, for example, 3 people and we had like 20 candies, right? Like what would we do? Like this would need to be like 6.67 and this would need to be 6.67 and this would need to be 6.67. But we're dealing with integers here, so that just doesn't work. Otherwise, well, what do we need to do? And the answer is that every element that either doesn't have enough candies or has the exact amount equal to the average is already fine. And we don't need to take candies from them because in the redistribution, they're either going to gain candies or stay the same. Because if we remove candies from them, or if they end up like losing candies overall, then because they already had less than or equal to the average, they'll be guaranteed to have less than the average. So they can't lose candies. And so because they can't lose candies, we might as well not give any of their candies away, because like we don't need to. Yeah, and so the way that will work is, so the only guys we care about are the guys with more candies than the average, like strictly greater. So essentially the answer is, and also every guy with strictly greater amount of candies needs to give some of them away, because if they don't, they'll have more than the average, and so like you can't get rid of them. You can only, in the redistribution, you can only give someone candies. So you have to redistribute their Whoa, Jesus! You have to redistribute their candies, and yeah. So essentially, for each element, if it's greater than the average, you take it, and if it has less than or equal to the average, you don't take. You don't need to take, and you shouldn't, because you're trying to minimize the amount you take. So yeah, and so basically what that means is we count the number of values that are greater than the average, and then that's the answer. So in this case, we have this value s. We're going to read in the value and then take the sum of the whole array. And then again, if s is not divisible by n, the average is not an integer, so we can't achieve it. Otherwise, we count the number of elements that are greater than the average, which is of course the sum divided by the number, which is the definition of average. So cool. And now we continue. Now we go to C. I feel like I could be hacked on D, because like I'm getting hacked on just every single div3 that ever existed. So cool. Very cool. In this case, this is what I messed up on, because you can basically do it in any way, and I did it in a wrong way. So yeah, you have an array of integers. You want to find the number of pairs where the sum is greater than or equal to the, or where the sum is in a range. It's like, for example, with 5, 1, 2, and then L equals 4, R equals 7. The valid pairs are 5, 1, which have sum 6, and 5, 2, which have sum 7, but 1, 3, 1, 2 has sum 3, which is not allowed, so there are only 2 valid pairs. Right, so like this can be done in a million different ways. Probably the easiest is with binary search. Because we're looking for the number of pairs, we don't really care how the elements are ordered, so we might as well assume they're sorted. So we can do, for example, 1, 2, and 5, so we can sort them. And then there are a million ways you can do this. So one way is to assume this is the larger element. And then we like iterate over the larger element. So we say first that the first element is the larger element, then we say the second one is, then we say the third one is. And that way, when we say this is the larger element, the candidate smaller elements are everything in this prefix. But this prefix is also sorted because we sorted the whole array. So if we want, let's say this is AI, and we're looking for some AJ that work, or we're looking for the number of AJ that work. So if we want AI plus AJ to be between L and R, then because we already know what AI is, now we're looking for the constraints on AJ that work. So we subtract AI from everything. And now we just simply need the number of elements in this prefix that are in some certain range. And this can be done in a million ways using, for example, binary search. I did something dumb. I used an ordered set, which is like a C++ built-in thing. And the problem with it is that it doesn't handle equal elements right. So if you have equal elements, it just like doesn't store them. It only stores one copy. So the way to fix that is to use something like less equal, which is why I got that wrong answer. But Yeah. So essentially, you just need to find the number of values on this prefix, like anything smaller than AI that work. And you don't consider the larger ones because, say you like, for example, this pair works, then when you consider this one as the larger element, you'll also count this pair again. And so you'll count a pair twice. So you don't want to do that. So you might as well just assume AI is greater than or equal to AJ, and then just count them that way. Or like the index, like we can assume I is greater than J. I think they do it the other way, but whatever, it doesn't matter. But yeah, that's the idea. On this prefix binary search, do any sort of algorithm to count values on a range. Like, basically anything works. Anything except for what I did. Okay. In this one, we have two numbers. We have A and B. In one move, we can pick an integer C. And then we pick one of the numbers A or B, and then we either divide A by C or we divide B by C. And it only works if the division works. If A is divisible by C, then you can divide A by C, or if B is divisible by C, then you can divide B by C. But you can't divide a number that it's not divisible by. And also, like, C has to be greater than 1, meaning you can't stall. So what you want to do is, you want to make A equals B in exactly k operations, where like this division is one operation. So you want to see if it's possible or not. You don't need to print the operations, although it would be possible to. So actually, it'd be annoying too. So let's just savor. Let's just what's the word? Relish. It's like just enjoy the fact that you don't have to, because that would be really annoying otherwise. So this problem is much less annoying than I thought it was, and the reason is there's only like one edge case. So if k equals 1, then it's sort of hard, because like let's consider only k equals 1. So if a equals b, you have to divide one of them by c, and you can't not divide. You have to decrease one of them by dividing by c. So if a equals b, the answer is actually no, which is sort of unexpected, but that is the way it goes. And then otherwise, because you only have one move, like one of them has to be a multiple of the other. Otherwise, there's nothing really you can do, because like there's only one move. Yeah, so the only way you can do it is if A is a multiple of B or B is a multiple of A, because you only have one move, so you can only divide one of the numbers. So if A mod B is equal to 0 or B mod A is equal to 0, in fact you can replace this with XOR, and that would merge these two cases into one. I'll leave you to work that out for yourself why that works, but yeah. Otherwise no. So if k equals 1, if a equals b, no. Otherwise, if one of the numbers is a multiple of the other, then yes. Otherwise, no. So what I'm saying is you can replace this with XOR and then remove this check, and then this would actually be the same thing. So otherwise, k is greater than 1. And in this case now we don't need to worry about a equals b, because we can do it in two moves, always. Sort of, actually. Actually, there is the case of a being 1 and b being 1, in which case we can't do it in any amount of moves, but that'll be handled. So now, for example, suppose like a equals 7 and b equals like 243, right? So these are like totally irrelevant numbers, but in 2 moves we can make them equal because we simply reduce them both to 1. So like it's sort of easier to have more than one move because now we don't have to worry about a equals b. Because in a similar note, if they're both 7, then we just make them both 1. But what if we have like k equals 3 and then they're both 7? Then in one move we're forced to reduce one of them to 1, and then we're forced to reduce the other one to 1, and then we can't do anything else. We're out of operations. But we have to do an exactly k, meaning that like we can't. So now the trick is we consider the prime factors of the numbers. I don't know why they had 10 to the 4th. Couldn't they just be like nice? So for example, with the prime factors, say we have 36 and 48 as in the first sample. So 36 is 2 times 2 times 3 times 3, and 48 is 2 times 3 times 3 times 3. Wait, no, is it? 6? No, it's not. It's 2 times 2 times 2 times 2 times 3. Yep, makes more sense. Right. So every move we can kill exactly. Every move we have to kill at least one of the prime factors from one of the numbers. So every move, for example, we can kill this or we can kill this, but we have to kill something. So that immediately gives us an upper bound on the moves. It's the size of the factors. It's not a word. I don't know what I'm writing. It's the size of the factors of A. And this like bar notation means the size of something. And then it's the size of the factors of B. Now look, here's some contest strategy. Because this is a div 3, you can reasonably guess that this upper bound is like fine. And then you can sort of guess that there's a sequence of moves that will work as long as you don't have more than this upper bound. So if k is less than or equal to this upper bound, you don't necessarily have to prove that there exists a sequence of operations. You just have to believe. Again, some contest strategy. Like, it's like sort of the art of guessing. And so, yeah, like you can reasonably believe that if you don't have too many operations, then there exists a sequence that works. And this just turns out to be true. So if k is greater than 1, then the only condition is that k is less than or equal to this upper bound. That is, if you don't have too many operations, then there exists a sequence that works. And in fact there is, and it's like really simple. Say k equals 7, or let's start with this. Say k equals 3. First, we kill this. We kill one prime factor. Then we kill everything else, so we make this 1. And then we kill everything else here, so we make this 1. So in general, say k equals 7. So then we can kill this, 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 and then we can kill this. Right? So that's the idea. And in general, the way to do this is, in fact, there are a lot of ways to construct an algorithm for doing it, but one simple way is we say that everything except for the first prime factor is like free. So while k is greater than 2, then like kill one of these and then reduce k, and then do that until k equals 2. And then when k equals 2, because we saved these factors, we have them again, and so now we can remove everything from both of them and make them both 1, and then they're equal. If at least one of these numbers is 1, the algorithm is like similar. In fact, it's very easy to prove because now it's just the number of factors of the one that isn't 1. And if both of them are 1, then then the upper bound is 0 and we can't do any operations, so we get it correct. So really, like, if k is greater than 1, then we can always achieve this upper bound. And like I said, the reason, or I don't know if I said it, but the reason this is the upper bound is because like every time we have to kill one of the factors. So this is the most operations we can do, because when we run out of factors, we can't do any more operations. So the only condition is that k has to be less than or equal to this upper bound, in which case yes, otherwise the answer is no, because you have too many operations. So there are a lot of ways to get lost in the casework, and in fact there isn't much, but there could be. Depends on how you set it up. So my check was print if k equals 1, special case. So if one of them is divisible by the other and they're not equal, print yes, otherwise print no. And in this case, you just check if this upper bound is greater than or equal to k, and if so, print yes, otherwise no. And I used like a number theory template to find factors. In fact, I want to see how the time limit was on this. Did Neil do it? What was this? Okay, 592. Look at a couple of other people too. I just want to make sure like the time is fine. 546 and oh, he did it fast. Okay. Well, Neo and Maxine, they did it pretty slowly, so that's fine. Hopefully we'll be fine on that. I just don't want to be hacked again, because I've been hacked so many times with these. And it's sort of sad how many times I lost first and I also lost fifth because of some like dumb post-contest stuff. So I mean, ideally that wouldn't happen again. Yeah, would be nice. We're spending a lot of time on E. It seems like a pain to do. I think skipping E and going for F and G first was the move. Yeah. Okay, E. Now that we're doing the editorial, I don't really have to skip problems because I know everything. So I'm a magical god of wisdom, so I can explain everything. In this problem, you have to simulate a programming language. There are two things you can do. You can set variable x to string y, or you can actually both of them are set, so or you can set variable x to variable y plus variable z. So you can set variable x to the string y, or you can set it to y plus z. Or you can set it to the what was I gonna say? I was gonna say you can, yeah. So these are the two operations. Like you can either add, and these variables are all strings, right? Because the only set operation is a string. So how does this work? What am I saying? Yeah. So you add two variables and then set them at x. And I think you can even like add two variables into itself. Like you can do x equals x plus x. And yeah. So what you want to do is, in the end, this program is going to have some final statement. Like for example, you'll have some final statement: set a equal to b, or like set a equal to b plus c. And what you want to do is, sorry if that was really loud, in this final statement, you want to find the number of occurrences of haha like just the string haha, in the final variable. So the problem is you have up to 50 statements, and in fact, I don't know why they have that bound. It could be much larger, but the problem is, say we have something like this, x equals x plus x. So if we do that 50 times, then we'll have 4, then we'll have 8, then we'll have 16, we'll have 32, ... And then we can in fact have a string of, like the strings can be up to length 5. So we can do 5 and then like multiply it by 2 50 times, actually 49 because we have to do the initial assignment. So the worst case like string length is 5 times 2 to the 49th, which is enormous. Let's just look that up really quick. It's 2.8 times 10 to the 15th. So if you want to store these strings in memory, it's not happening. It's not happening. We need a better way. And so the key is, the problem is the addition operators. The assignment is like fine, it's not really a big deal. But the addition is sort of a problem. And so the way we handle it is, consider what happens when we set x is equal to y plus z. What we're going to do is we're going to maintain the number of ha-has within each string. So really we store each variable as a pair. We store for each pair, or we store for each string the count and the string itself. So for example, like the string ha 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 would map to the pair 2 because there are 2 instances of haha, and the string itself. Except this still fails because of memory limit exceeded. So we can do better. Let's consider merging 2 strings together. So merging 2 strings is, if we merge 2 pairs of count string. So for example, consider the first count and the first string, and we merge with C2 and S2, representing the second count and the second string. So what pair do we get? Well, the string is of course S1 plus S2, that's simple. But what about the counts? So we get C1 plus C2 plus not the number of like ha-has in the new string, but the number of new ha-has. And then S1 plus S2. So really, all we need to count for each merge is the number of new ha-has. And so the question is how to do this. So let's consider now we're concatenating 2 strings. One of them is like this, the other one is like this. And we're only counting the number of ha-has that cross this barrier. Right? So how many of these ha-has could there be? Well, we can use 3 characters from this side and 1 from this side. Or we can use 2 from both sides, or we can use 1 character from this and 3 from that. But look at that, that's like a really small number, right? Like imagine, there are at most, and not even that, but there are at most 3 new ha-has when we stick on a string. So as a concrete example, take for example merging ha and aha. So the first possible move is taking 3 from this side and 1 from this side. In this case, we do get haha. And if we take 2 from both sides, we get which is not valid. And then we get another haha when we take 1 from this side and 3 from this side. And there are no other cases. If we take 4 from this side, then it's not a new one. We already counted that in this string, and same for here. So the only cases are where it crosses this middle barrier, or this middle border, and there are only 3 possible cases. Another thing to note is that it only uses the last 3 characters of this string and the first 3 characters of this string. We don't care about the other ones because they couldn't possibly form new characters, or they couldn't form new strings. So now what I propose is this sort of compressed format. And what the observation sort of is that we only care about the first and last 3. So why would we bother storing, like, let's say we have this like super long string. Right? Like just this absurdly long string that I bothered to write out for some reason. Why would we bother storing all this when we're doing a merge, we're only caring about the last three? Or when we're doing a merge on the other side, we're only caring about the first three. So instead of storing the entire string every time, we might as well store it in a compressed representation where we only store the first and the last three characters. So this entire string, because all of this is not relevant anymore, all of this is not relevant to counting merges, to counting the number of new ha-has we get, we only store the first and last three characters. So the compressed representation is this. And then when we merge, instead of storing S1 plus S2, we store the compressed version of S1 plus S2. And then we compress every time we merge so that every string is of length at most 6. And in memory, that means we only have 50 variables and each string is length at most 6, so it's like it's totally fine now. It's like 300 memory. Right? So everything works out. And so now counting the number of new ha-has is easy. We simply enumerate over the positions. Like here we said we would take 3 from the first and 1 from the second, or we take 2 from the first and 2 from the second, or 1 from the first and 3 from the second. We just enumerate these possibilities and we check if each one is a ha-ha. And then, so to merge these, it's simple now. So that's basically it. Now, another hard part is sort of implementing this idea. And so, because the input is like, it's literally a program. So, certain languages have a nice way to deal with this. I think C++ also does too. Because it'll read things space separated. So like, for example, it'll read this colon equals as one thing. So C++ reading in this line, like if I did like b colon equal aha, then I'm going to read this separately into 3 strings. If I did something like cn to z, for example, I'm writing out code by hand, which is stupid, but it would read them into like 3 separate strings like that. So it sort of makes it nice. So first thing to do is I map each string, like each variable name, to a pair of the count of ha-has and the string. Oh, and also, because each merge only adds at most 2 new ha-has, actually no, that's not right. But like we can merge 2 things with a lot of ha-has and it can get exponential. But the number of ha-has is at most like the length of the string, which is again 5 times 2 to the 49th, which is still a huge number, but it fits within a 64-bit data type like long, so we don't need to worry about overflow, is what I'm saying. So we map each variable to a pair of the count of ha-has and the compressed string. I called it shrink in this case. Then we read into the number of commands. And I'm just keeping track of the last one here so that I can print that eventually. So right now I read in the first 3 strings of a line. And then because we have like a distinguishing factor here, we have colon equal here, but we have equal here. So if the second string is a colon equal, then we know it's an assignment, and otherwise we know it's a like addition, concatenation. So if it's an assignment, we simply like just designate a variable to A, saying that it's equal to the representation of it. So we count the ha-has in it, and then we compress it, although we don't really need to compress it because it's fine on its own, so it doesn't matter. And then otherwise, we know it's an assignment, so now we need 2 more variables, so we read those in. Then we're setting A equal to C plus E in this case. So we take the representations of those 2, then initially we add their counts, but then we also need to add in the new counts we get from merging them, and then we also need to take the compressed form of their like concatenation. And so the way the shrinking works is I made the shrink also work for like counting even strings that aren't merged together. So like the initial string is just counting the ha-has in them. So the way it works is it takes in a string, and then it also takes in the split point like as a number, so that I'm saying I'm merging these two. And then we just count the number of ha-has that merge over these split points. And then we merge them into one big string, and then if the string is long, then we only take the first and the last 3 characters. But if the string is small enough, it doesn't matter. In this case, I used 5 instead of 3 just to be safe, but like I'm pretty sure you can get away with using 3. It doesn't matter that much, like it's still very fast. And yeah, so the remaining part is just counting like the barrier characters, and it's just like indexing. And so yeah, I sort of like in a hacky way, I made it also so it counts the assignment. So for example, if I wanted to count the ha-has in like this, where there's no splitting point, so it's like an assignment, it's an assignment instead of a merge, I just set the midpoint to the middle, and that way it would still like count everything. So I'm just like going over implementation details at this point, but yeah, everything sort of works out. It's not as bad as it might seem. If you're still confused, you can also keep looking over code. Alright, that was the worst one. Now this one's like a lot simpler. Basically we start with a number like 5, and then we're going up to a number that's larger than it, for example 12. Yeah, and then so we go from 5 to 6 to 7 to 8 to 9 to 10 to 11 to 12. And then what we're interested in is the number of digit changes. Actually, I'm not going to make this 5. I'm going to make it like 8, because that's less annoying. So we start with 8. Well, I'm going to write it as 08 because we care about all the digits. Then we go to 09. Then we go to 10. Then we go to 11. Then we go to 12. And we're interested in the number of digit changes. So in here, the only digit that changes is the ones digit. But here, both digits change. This one increases and this one resets to 0. Then this one only 1 changes and this one only 1 changes. So we're just in the total number of digit changes. So in this case, this number would be 1, this would be 2, this would be 1, this would be 1, so the answer would be 5. Right, so now how does this work? And the way it works is, oh, and also the number is up to 10 to the 9th, so we can't like simulate it, of course. But let's count like, it also mentions that every time it's always a suffix that changes. And this is just like true. For example, if we have like 3999, then when we increment this, it'll become 4000. And so every digit that's a 9 gets reset to 0. And then the final digit that's not a 9 gets incremented by 1. But it's always a suffix that changes. I would recommend keeping this idea in mind. So yeah, so what happens is, how many times does a digit change? Or rather, how many times does a suffix change? So for example, like, how many times does the suffix of length 1 change? How many times does the suffix of length 2 change, etc.? And so length 1 is simple, because every time you increment, the suffix changes. But also, because it's always a suffix that changes, you know that every time this digit changes, everything after it will also change. So the number of times this suffix changes as a whole is simply the number of times that this digit will change. So let's take a bigger case, for example. Let's go from like 252 to 477. So the number of times that the ones digit changes will be 477 minus 252. Then the number of times the suffix of length 2 changes is the number of times, actually I think it's plus 1? No, it's not. The number of times the suffix of length 2 changes, for example this or this, is the number of times that this digit changes. And how many times does this digit change? Well, if we sort of drop off the last 2 digits, then now we're interested in how many times do we go up to get from 25 to 47. Because we go from 25 to 26 to 27, or rather we go from 250 something to 260 something to 270 something, but we don't really care about the something. And then eventually we end up to 470 something. And so it's the same formula. It's the same idea, except we just dropped off the last digit. So we add an additional 47 minus 25, because sometimes when this changed, this also changed. So we add in the number of times this digit changes. And then how many times does the largest digit change? Well, it's the same idea. We go from 2 something something to 3 something something. I don't know what that is. That's not a letter. To 4 something something. Right? And so that's the number of times that this digit will change. And it also changes the whole suffix, but we already counted the number of times these 2 digits change. So really we just need to add in this digit, and the answer is 4 minus 2. The number of times this increases. So the algorithm is very simple. We just consider every digit and see how much it changes. And the way to do that is we drop off all the digits that are before this one, and then we consider that. And so notice that it's equivalent to, like, we're considering 252, and then we're considering 25, and then we're considering 2, and we consider 477, and then we consider 47, and then we consider 4. But dropping off a digit is equivalent to, like, setting x to the floor of x over 10. Because like we divide it by 10, meaning we keep this part, and then it becomes like 25.2, for example. And then we just drop off the decimal, so we get rid of it. And then that means we drop off the digit. And so floor is very nice because it's integer division. It's how most languages handle division by default. So the algorithm is add r minus l to the answer, divide both by 10, repeat. So code-wise, it's insanely simple. You just, in fact, we don't even need this. We can swap the order of these 2 statements, and then we don't even need that. So we just set the answer to the difference between the 2, then we divide by 10, and then we add that, and then we divide by 10, and then we add that, until we're done. It's kind of magical. It's also why people solved it so quickly. I'm fairly sure it's standard in that it's like shown up before or something, but a lot of people are solving this, and not many people are solving E, so yeah, it's just gotta be how that works. I think it's just a lot simpler than might be expected. Yeah, people are having a fun time with this. Final step, problem G. This one's also like relatively simple to explain, I guess. The code isn't that bad. I just sort of messed up part of it. So we have 4 integers, x, y, a, and b. So we have x gifts of type 1 and y gifts of type 2, or like red and blue, whatever. And then what we can do is we want to distribute them into like gift baskets. So each gift basket can either have, I'm going to use red and blue. So we have initially x red and y blue. Though I'm not going to use this color scheme the whole time because that's too much effort. So each basket can either have A red, like A red, what is it, candies? And B blue candies. Or it can have B red candies, so we swap the 2, and then red, and then A blue candies. So we need to find out the maximum number of baskets we can take. Okay, so first, without loss of generality, assume A is less than B. It just makes it easier to like have one be smaller than the other. And if A is greater than B, then just swap them. So like in code, like this is just what I do to assume that one is smaller than the other. Like if one of them is greater than the other, just swap them so that they don't greater, and then everything works. Yeah. So the hell is that? Okay. There's no way I'm gonna write this well. This A is gonna be ugly for the rest of time, but it's kind of bothering me. Okay. So how does this work? First strategy, binary search, because it's like definitely binary searchable. If we can make a certain number of gift sets, then if we remove one of the gift sets, it'll still be possible because now we just use fewer candies. And if we can't make some set of gifts, then if we require us to have more candies, there's definitely no way we can make more. So it's like monotonic. There's some value x such that everything less than or equal to x works, and everything greater than x doesn't work. And so we can binary search on the point that it works on. I'm not going to explain the intricacies of binary search here. I think there are a lot of nice videos, for example, like Rick does, but yeah, you can search those on your own. So now how does this work? What we need to do is we need to figure out, is some x possible? No, let's not use x. Okay. Let's use m. So can we make m baskets? My handwriting is like very interesting right now. But yeah, can we make m baskets? I don't know what's up. Just like tablet writing, I guess. It's less resistance from the pen. So how do we check this? Somehow we have to figure out which type we make for each one. And like we can't do greedy because, like, for example, say we have like 6, like x equals 6, y equals 4, a equals, I guess maybe we can greedy, but also at the same time, it's like not that great of an idea. It's probably better to just like not try. So instead what we can do is we can do like a different type of greedy. We can do like a smart greedy that's like sort of not greedy. So remember we assumed a is less than b, or less than or equal to b, I guess. Are they different? They might be the same. Yeah, so because we assumed a is less than or equal to b, because we need to use at least a candies in each red or blue no matter what, like in this case we use at least a, and in this case we use at least a. For every basket, we use at least a red and blue every time. So we might as well subtract that out now. So the first step is we say x like minus equals x times, or it's like the number of guaranteed red we have to pay. And we also have to subtract out the number of blue we have to pay, which is also m times a. Note that this is not b, which is a mistake I made before. It's always a. Right? Because that's something we have to pay no matter what. In any configuration of baskets, we have to like use at least that many. And so the question is now, which one do we use b on? And that means that we get an extra b minus a for each one. Yeah. So which one do we use b on? So then if we use b, then we pay an extra b minus a. But now it's sort of more clear what we should do, right? Because it's either going to be cost 0 and b minus a, or cost b minus a and 0. And so the key is that the other one is always 0. So now we're interested in the number of times we can use b minus a on the left, which is simply this new x divided by b minus a. Right? Because, like, we want to do this as many times as possible, and it doesn't hurt the other element, so it's okay to do it greedily like this. And so the number of ways we can do it is simply like the number of times we can do it. Or the number of times we can do it is the number of times we can do it before running out of candies. And here it's the same idea. The number of times we can do it is y over b minus a. So the number of baskets we can make in total with this constraint is the sum of these two. And also, like, these both have to be greater than or equal to 0, otherwise it's not possible initially, so it definitely won't be possible later. So then this is the new number of baskets we can make. If b equals a, then like b minus a is equal to 0. So you can assume these are infinity, because like these costs are 0 anyway, so they don't really hurt us. So if b equals a, it's already possible. But if b is greater than a, then this is like when we consider. And then we have to, this is the maximum number of baskets we could ever make. So this number has to be greater than or equal to the number of baskets that we say we're making. And if that's true, then it's possible for m, and otherwise then it's not. So first, after we subtract m minus a from m times a from x and y, they both have to be at least 0. Otherwise we can't do it initially because we're forced to spend at least a. And then we consider the extra that we have to pay, and we assign them to whichever one we can do. So code-wise, first we do the binary search. We check, for example, MB. Now I use just like two new variables, XX and YY, that represent like the new X and the new Y. So it's like, for example, A times M, B times M. Then we check if both of these are greater than or equal to 0. Then if B is equal to A, then we know it's already possible. But if B is greater than A, then we have to check this extra condition. And then we simply say, if the number of baskets we can make is not enough, we say it's not possible. Otherwise, it will remain possible. And then binary search, and then we subtract 1 because of indexing stuff. The whether you should subtract 1 or not is also dependent on how your binary search works. But the easiest way I find is to consider the last step. Like, for example, we have L is equal to R minus 1. So we have two things. And then we're considering this one. And then we say, if this works, then what do we set the mid to? If it works in my binary search, we set it to this. And if it doesn't work, we set it to this. So if this works, we set it to this. But we already know this doesn't work. So we have to subtract 1 because this doesn't work, but we know that that works. And if this doesn't work, then we just said this doesn't work. So the answer obviously can't be this. But we know this is the smallest one that doesn't work. So the one right before it does work. You can also reverse the binary search. It really doesn't matter. But that's the idea. Yeah. Is there a different way to do it? If it's not possible. I wonder how that works. I don't have anything else to say about the problem. I'm thinking about binary search now. Why does it work sometimes, but not like all the time? Oh, right, okay. It's because the answer you want is on the left, not on the right. Ignore what that was. I'm just wrestling with my own thoughts. Yeah, so that's cool. there is a very decent chance that something could be hacked. For example, my problem D submission could be hacked because it's sort of not far. It's the closest to the time limit. It's not that like close to it, but it's like a constant factor off, so it could be scary. And some other people get TLE. Wrong answer. TLE, yeah. Wrong answer. What did other people do? Wrong answer. Wrong answer. Okay, not that many TLEs, I guess. Oh, this guy got TLE. TLE, and then wrong answer, like, very early. Okay, anyway. Another wrong answer. I'm just checking everyone. TLE because of Kotlin, probably. Kotlin, whatever. And then, yeah, wrong answer and TLE. So that's fine. I'm not sure about other problems, like maybe, but hopefully not, because I don't know. It's always a TL issue. It's always a time limit issue with these. So I don't know. I mean, whatever. We got 4th in principle. This is technically my best rank to date because I lost the first, even though it was still like fair. It was sort of like a complication with how the system worked. And it was more like it was too much effort to fix than it wasn't like correct. So yeah, whatever. 4th is very good though. So yeah, I'm happy. Hopefully this went well for you guys too. Although if it didn't, that's okay. You can always take it as a learning experience. And look at the dashboard every once in a while. It tells you what to do. It like if F has an order of magnitude more solves than E, try F. Like a lot of people are finding this easier. And in fact, this is the hardest one just because of its implementation difficulty, probably. So yeah, hope you enjoyed. Hope you got what you need out of this video. Hope the audio isn't too bad. I can see it being like way too loud. So I'm gonna try and calibrate a bit more, but hopefully it's like actually working now. That'd be nice. If it just like, if it was audible, because for a long time it's been too quiet. I also just realized it's been a long time since I did a screencast, so I forgot to update the subscriber count. But I can do that now in sort of retrospect. Yeah. I guess I'll have that for next time. Alright, well that's it. I don't have anything more to say. I'm just stalling at this point. Goodbye.